Hi, this is Paul from Foresight Tech. In this video, we are going to deal with the comparison test, which is a method to test the convergence or divergence of a positive series. Let's see the outline. First, I will introduce the comparison test, including direct comparison test and the limited comparison test. Then we will practice 4 questions together about how to use the comparison tests. Let's see the material. Here we have this type of questions. How to test the convergence or divergence of a series. Okay, so far we already learned 2 special types. The first is a P-series. The second is geometric series, right? So if your series is just a P-series or geometric series, of course we already have results, okay, to follow. So let's go over a little about the results. P-series. And the P-series, which means the general term is 1 over n raised to the p's power, right? Okay, so p is just the power to the denominator. Keep in mind. So the P-series converges if the power p greater than 1, and the divergence if the power p less than or equal 1. And for geometric series, of course, we have this term, and converges only if the absolute value of the common ratio less than 1, right? Which means r between -1 and 1, and the geometric series converge. Otherwise, diverges. Okay, so these are the results for the 2 type of series we learned before. Now, if we have a new series, okay, how do you do? Of course, we have this obvious strategy. Okay, it's like this. If your new series is related to P-series or geometric series, and of course, we try to use a method we call the comparison tests. Okay, we will try to use the results from P-series or geometric series. Then we have 2 types of comparison tests. Okay, direct comparison test or limited comparison test. Let me introduce the first. Here is the first type of comparison test, direct comparison test, or we simply say it's comparison test. And suppose now we have 2 series, and we have this condition, which is the major condition. Let me highlight. Okay, so first, both series are positive series, right, greater than 0. And then is an less than bn for all n terms. What does this mean? This means each term in A series is no more than the corresponding terms in B series, or like A1 less than B1, less than or equal to B1, A2 no more than B2, A3 no more than B3, like this, all the terms. Okay, so this we call the comparison. And the results is if B series converge, and then the A series converges. Or B is if A diverges, and then B series also diverges. Okay, so these results, usually we can see these results in another way. Okay, if we say A series is the smaller series, and the B series is the larger series, then now, see, let me write it down. And for A, we can say in this, for A, B series converge. So B is the larger one, right? So usually we say is a large series converges. And then what? And then AN is the smaller series. So we say smaller converges too. This makes sense, right? Okay. And for B, it's just the converse. See, if A is divergent, okay, smaller, right? So we say smaller diverges. And then we have a result. B is the larger, so larger diverges too. The larger series diverges too. Okay, and in in this way, we easy to see the results. Now let's prove. Okay, and we go to the first, and for A, how to prove? And suppose B series converges. How do you say A series converge? So far we have one rule, right? Is the definition. We need to use the partial sum sequence converge to. Okay, we need to look at the partial sum. Let me write down the partial sum, which is Sn, right? Okay, and this Sn is the partial sum for A series. So I wrote in this way: I from 1 to n A I. This is the partial sum for A series. And how do you say these converge? But we can control, right? Can you see, is this right? Because each term AI is less than or greater than or less than or equal to BI. Therefore, and the finite terms, the AI added together is less than the finite terms of BI. That this makes sense? Okay, and then what do we do? For these finite terms, of course, is less than infinite terms, or the BI added together. Why? Because BI is a positive series, as a positive number. Okay, and in this way, what do we do? Can you see the sequence Sn now is bounded above? We can see this sequence, partial sum sequence, is bounded above, right? Okay, and then another we can see Sn because it's B as a positive terms, or A is a positive terms. Can you see this? Because A is a positive terms, so we add the more terms, we get a bigger. Therefore, the sequence Sn is increase. Okay, it's a monotonic, right? It's increase. Let me simplify in this way. Okay, therefore we have these two results. And the partial sum sequence is bounded above and also increase. Do you remember results? Okay, we call the monotonic sequence theorem, right? The monotonic sequence theorem, let me write. So now is by monotonic sequence theory. What do we do? And the sequence Sn is converge. Therefore, the series An is converges too, right? See, this is the proof for the first. Let me go into the second. So how about the B this time? B is what? B is a smaller, which is the smaller diverges, the bigger diverge. Look at the obvious, okay? The smaller diverge, this time is goes up into infinity. So the bigger one, the larger one, of course, goes up into infinity too, right? Okay, so how to write? Excuse me. Let me write in this way. We still look at the sequence, okay, the partial sum sequence. This time we need to prove for B, so let me write this partial sum sequence for B, which is BI. Can you see each term B is what is the larger one, so greater than or equal to the small. Small is AI, I from 1 to m. Okay, and the AI, the series diverge, which means the partial sum diverge to what? Diverge to infinity. Does it make sense? Okay, therefore, what do we do? And Sn is greater than another series. We have a comparison, right? So when we learn the sequence, okay, therefore we have these results. Sn diverge into infinity too. Okay, and this is important. So can you see? Let me highlight. Sn, the partial sum diverge into infinity. So what the results? And therefore the series diverges too. And that's the proof. Okay. And now let me introduce another version, the second type of a comparison test. Here is the second type. We call the limit comparison test. And this version is popular than the direct comparison test. Let's see. And suppose we have two positive series, A and B. this time we do not need to compare directly. What we need to do, let me highlight this condition. All we need is just look at the limit. Okay, if the limit points to a positive number like a 1 or 2 or something, and then we say these two series is at the same level or the same magnitude. Okay, therefore both converges or both diverge. Imagine if our series is A, and all we need to do is find a comparable series B, and then check the limit. Okay, if the limit points to a positive number, and then if B series converge, and then our series converge. If B series diverge, then our series diverges. Now let's prove it. And how to prove? And we need the direct comparison. Okay, we need to compare A and B directly. But how? We have to use the precise definition of the limit. Okay, let me draw you a graph so we can have a basic idea. Okay, let me draw like this way. And if I put a 0 here, C is a positive number, right? So I can put a C here. And now I look at the limit. The limit points C points this, which means what? Any epsilon number neighborhood, and the sequence can fall into the epsilon neighborhood, right? What does that mean? Let me show you the neighborhood. If I put this number and this number, let me highlight the neighborhood of C. Okay, and the radius is epsilon, any epsilon. Okay, and this one, what do we have? We have an over bn. This sequence will fall into the neighborhood when n large enough or greater than a capital number n. Does this make sense? So that's the definition. Because any epsilon, we can do this. Okay, I will pick epsilon small enough so that this left endpoint is a positive number. Why we need to do this? Because later we do direct comparison. Okay, so we need all positive sequence. Okay, can we do this? Yes. How? I pick epsilon small as this C over 2. How do you think this time? Okay, the left endpoint should be C over 2, right? The right endpoint should be 3C over 2. Can you see? Okay, this time fall into a positive, okay, neighborhood of C. Let me write in language is this, which means given any epsilon, this time we pick epsilon equals C over 2, right? And we can find or exist a capital number n, and so that or such that if n greater than capital N large enough, then and what the sequence fall into the epsilon neighborhood, which is n over bm minus c, absolute value less than epsilon. So this is the precise definition. And then let's change this neighborhood into this language, which means what? Which means an over bn. See, and from this graph we can see n bn should be between the left endpoint and the right endpoint, right? So which means this greater than c over 2, right? Less than 3c over 2. Good. This is kind of a direct comparison. Okay, of course, we change it to this version, and we do this, and we times bn all the sides, 3 sides, because bn is positive, so we do not need to change the sign, right? Therefore, we can write in this way. So c over 2 times bn, right? Less than an, less than an is less than 3c over 2 times bn. They are equivalent. So now what do we have? Okay, let me highlight this. We have two comparison. Here is the first. let me put this we called 1. And we have the second comparison, which is this part, right? So let me call 2. Okay, so now what do we have from the first? Okay, can we see from the first? Okay, what do we have? We have because Bn is greater than An. Okay, this constant number, positive number does not matter, right? So Bn, if Bn converges, the large converge, and the smaller one will converge too, right? Okay, let me write this. Based on the first one, we have these results. If Bn converge, and we can find what An converge. Does this make sense? That's based on the direct comparison. Of course, probably you will ask, and this direct comparison only for n large enough. But don't worry, okay, because finite terms will never change the convergence or divergence. Okay, so this should be correct. And then the same, based on the second comparison, direct comparison, what do we have? Let me write. So based on the second, see, if Bn this time is a smaller one, if Bn diverge, what do we have? An diverges too, right? Okay, let me write. Which means if Bn diverges, okay, so we can find An diverges too. Do you think this is the proof? Yes, we do. See, Bn converge, An converge, Bn diverge, An diverges. So that's both converge or both diverge. Okay, so this is the proof for this comparison. Now let's practice this comparison test. Here is the first questions. We need to determine convergence or divergence of this series. And this is a positive series, right? Not a p series, not a geometric series. However, I'm going to show you we can link this series to p series. Why? And remember, we have a limit comparison. And tell us is the limit n approach infinity, right? Imagine if n approach infinity, how about this one? This one just does not make any sense. You can just simply delete. See, if we delete this one, we will get a comparable series, which is 1 over n squared. This is the series we are going to use. Okay. How about this p series? This is p series, definitely. And p equals 2, right? Is greater than 1. Therefore, this p series is converges. Okay, so now I can make a conclusion. I say our series is convergent too. Why? Because the limit comparison test tell us about that. Let me show. So how do you say? I say I will use the limit comparison test. Okay, see, which is this way. We need to look at the limit of a ratio, right? 1 over n squared plus 1. This is our series. Okay, the general term. Over the 1 we need to compare, which is 1 over n squared. Can you look at the limit? And you know how to do. Let me simplify a little. Divided by fraction flip, which is times the flip, right? So we have n squared over n squared plus 1. Okay, and if we divided n squared both the numerator and denominator, see, what do we have? We have 1 over 1 plus 1 over n squared. And this term is 0, right? Therefore, it's 1 over 1. Easily to see. This approach to how many? 1. That doesn't make sense. Okay. And if we have these results, 1 is a positive number, not a 0, right? Okay. Therefore, the comparison limit test we can use. So we say because our comparable, this is p series converge. our series is the same level as this series. So what the results? Our series converges to. Of course, is by the limit comparison test. Okay, so this is the common way so we can do the comparison test. But if someone you like, you can also use the direct comparison. Let me show you how to use the comparison, direct comparison test. Or we say the second, if we simply say it's a comparison test. Okay, no big difference. Okay, so directly compare term by term. Can you see our term or series is n squared plus 1. I say our is less than 1 over n squared. Why? Because our fraction, this fraction has a big denominator, flip. Therefore, what? I have a smaller fraction. That does make sense? If the denominator is bigger, and then the fraction is smaller, right? See, this denominator is smaller, therefore the fraction is bigger. Okay, therefore what do we have? We have a comparison, direct comparison. Now we can use the first step, right? Direct comparison test. Because what? Because this term, this series, okay, the bigger, right? The bigger series converge. And so what? So the smaller is our series converges to. That doesn't make sense. Okay, if I wrote, see, what we use is just this. Because the big, or we say the larger series converges. Okay, so we have these results. The smaller converges to. Right? Okay, so this is the first questions. Let me show you another question. Here is the second questions. And look at the series. Our series is the positive series. Okay, and we do comparison. Okay, we use the same strategy I showed you in the first questions. Use the limit. How do you think this one? Of course, does not make any sense, right? Just delete. Therefore, we get a comparable series. See, this time the comparable series is this. Is n over n squared. And if we simplify, we get a 1 over n. Okay, this series you know is famous, right? This is what? This is a harmonic. Okay, let me see. Is the harmonic series. You know, harmonic series is what? Divergence, right? Definitely. Therefore, okay, so I simply get a conclusion for our series is also divergent, right? Because the limit comparison test tells us. Okay, let me highlight this. You know, this is what we need to use. Let me put and the complete steps. So how do you show your step? It is if I use the limit comparison test. Okay, like this, we need to do comparison, right? So our series is n over n squared plus 1 divided by the comparable, which is 1 over n. And you know, we need to find the limit. And what the limit? So simplify, which means times n. And then we go to n squared over n squared plus 1. We just did divided by n squared, both numerator and the denominator, right? So what do we have? We have the limit is exactly 1. Okay, now we can use because what? Because the comparable series diverges, and our series is at the same level with this divergence series, which means our series diverges too by the limit comparison test. So n over n squared plus 1 diverges. Does this make sense? Okay, that's all. we get it from the limit comparison test. Super easy. If somebody like a direct comparison, let me write here. Or you can do this way, direct comparison test. No big difference. Let's see. So for hours, which is n over n squared plus 1. How do you compare? Someone will say, yes, hour has the bigger. If I delete the 1, see, we will have this, right? Okay, and this simplified is 1 over n. Very easy. But this does not work. This type of a comparison does not work for us. Why? Because this is the larger series. The larger series diverge. Do we have a result for the large diverge? How about the small one? No one knows. The small probably converge, probably diverge. Which means what? This type of a comparison does not work for us. Let me show you. We have to do another way. Okay, we have to do another way. Be careful. Okay, and a little trick. So this time we need to do this. Okay, and this is how to do. And we want to get a smaller fraction, which means that we need to get a bigger denominator. How do you get a bigger denominator? I will increase 1 to n squared. Let me highlight. So we increase 1 to n squared. See, does this make sense? Okay, our series has a smaller denominator flip, but therefore we have a bigger fraction, right? Okay, good. And if we simplify, this is what? This is just sorry. So I get it somewhere not correct. We do not have a square, right? We do not have a square. Okay. So as dr goes to n squared. See. And what do we have? And we do have this. If we simplify, is 1 over not n, but 2 times n, right? Okay. Don't worry about these 2. The constant coefficient does not make sense. Okay, it does not change the convergence or divergence of a series. So what? See, now we have a comparable. The smaller one is what? Is a multiple of a harmonic series diverge. Smaller diverge, so the larger our series diverges too. Okay, so I can write because this 1 over 2. If you like, you can put 1 out of 2. You can factor out. See, with this, right? So this is divergence, of course. The divergence. So our series is n over n squared plus 1 diverges 2. It's the same, right? If I wrote a little, this, how did we get this? Because what? Because the smaller, right, diverges. So we get ours, which is the larger series diverges 2. And this is the direct comparison test, right? We get it. And here the second questions. Let's practice another question. Here is the third questions. And we also have a positive series. So how do you compare? And let's follow the same way. Okay, so imagine, and this n compared to n raised to the third power. When n goes up into infinity, this does not make sense. Okay, just too small. Okay, we did it. The same for this one. It's too small, right? Therefore, easily to see. So what the comparable series? Okay, so easy to get the comparable series is this, is n over n raised to the third power. And if we simplify, which is 1 over n squared. Okay, so you know why. This is a p series. Okay, this is a p series, and the p equals 2 greater than 1 is a convergent. Right? Therefore, we can get a conclusion. See, our series is convergent too, right? Because they are comparable. Okay, let me highlight. So this is the one we need to use. As DR, okay, write something. So how to write your answer? And we use a limit comparison test. Okay, we have to show the limit of a ratio, right? So n plus 1 over n raised to the third power plus m. So this is our series, and n divided by the comparable, which is 1 over n squared. And we're going to see the limit. If you times n squared flip, which is n raised to the third power plus n squared, right? And over n raised to the third power plus m. Okay, and then divided by n raised to the third power, both numerator and denominator. Imagine, what do we get? We will get this 1 over 1, which is 1. Okay, therefore the same, right? And our series is comparable at the same level with that convergent series. So I will show, because this series converges. Therefore, by the limit comparison test, so our series, no, sorry, it's not it. 1 is 1, n plus 1. This is our series converges too. Right? And the same, if someone would like to use the direct comparison, I'll also show you. If we use a direct comparison test, how to do. No big difference. Can you see? And the our is m plus 1 over n third power plus m. Okay, this time it's easy to do. And this is less than here. See, if we want to enlarge the fraction, and I have to do what? I have to decrease the denominator, which means I take n away, right? And also, how about this one? I can enlarge the numerator, which is m plus n. Does this make sense? See, 1 is less than n. Therefore, the second fraction, the right fraction is bigger, right? Also the same. And I take this n away. And the n raised to the third power is smaller. Therefore, the right has a smaller denominator. Therefore, it's still a bigger fraction. I hope you get this makes sense to you. And if we do this comparison, simplify is 2n divided by n, which is 2 over n squared. So that's the one. Direct comparison. Now what do we have? Because 2 over n squared, you can take a 2 out, which is over n squared. Can you see this p series? Therefore converge. Okay, and by the direct comparison test and the large converge, our series is smaller, right? So our series, the smaller converge too, which is the results. This converges too. This is the third question. Let's practice one more question. Here's the last question. And we still have a positive series need to test, right? So how to? We follow the same way. So we use the limit comparison, and therefore we can do what? We take 1 away, right? So let me take this 1 away. So we can find the comparable series. So this time is this way, 3n over 2n. And if we put them together, is this series, 3 over 2 raised to the nth power. What's that? Okay, F10, this geometric series, right? And R, the common ratio is 3 over 2 greater than 1. Therefore, is divergence. Okay, so the comparable divergence. We know our series should be divergence too by the limit comparison test, right? Let me highlight. So this one is the one we need to use. Let me write down something so we can understand. We by limit comparison test. Can we see? All we need to do is compare our series. The general term is this one over 2n plus 1 divided by, and the one we need to compare, which is 3 raised to 10th power over 2 raised to 10th power, right? And we change it a little bit. So what do we get? See, we definitely will get 2 raised to 10th power, 2 raised to 10th power plus 1 divided by 2 raised to 10th power, both numerator, denominator. What do we get? We get the limit is 1, right? As the previous question we did. So now, and because this series 3n over 2n is what is a geometric series we just discussed. This diverges. Okay, by the limit comparison, so our series, which is this one, diverges 2, right? So diverges 2. See, that's the limit comparison. Super easy to get. Or if someone like the same, I will show you how to use the direct comparison test. Can you see how to direct compare? Okay, we need this. This is our series, the general term. Imagine, as the second question we did, if we enlarge this by taking 1 away, enlarge this into 3 raised to 10th power over 2 raised to 10th power. Okay, so we will get that's a divergent series. The bigger one is divergent, so the small one we don't know. Okay, and therefore we need to use another. Let me show you this time how to compare. We compare in this way. Can you see? We need to get a smaller order fraction. How to get a smaller? By what? By increase this 1. Okay, let me highlight that. This is the trick a little. Increase this 1 to what? To 2 raised to 10th power. Increase the denominator, of course, we get a smaller fraction, right? And this time, what do we have? If put them together, I factor the 2 out. See, what do we have? We have 1 out of 2 times 3 over 2 raised to 10th power. Okay, so this time, see, what do we have? We have the smaller, right? So the smaller is geometric series, right? Let me see. And because this is a geometric series, and our common ratio is 3 over 2 greater than 1, so therefore geometric series diverge. And now we do have a result, right? The smaller one diverge, therefore our one, which is the bigger one, diverges too. Does this make sense? So this is the larger one, diverges too. Okay, so this is the answer for this question. That's all. Thank you. I hope you enjoy learning on this topic. If you have any question, please leave your comment. If you like this video, please give me a thumbs up. Thank you for your support. Please don't forget, you are very welcome to subscribe to my channel for more videos. In the next video, let's see. We were going to deal with the remainder estimate for comparison tests. Hope to see you there. Thank you. Have a nice day. Bye.